Heart disease is not the leading cause of death. Neither is cancer. It's actually infectious diseases that are far deadlier. Now, that's not true. It isn't. But it used to be, before the 1930s. You see, this is a graph comparing the causes of death in 1900s and the 2000s. As you can clearly see, in the 1900s, cancer paled in comparison compared to tuberculosis, pneumonia, or gastrointestinal infections. So then what changed? What was so different? What was so significant in the 1930s that changed everything? Well, it was antibiotics. And that's what I'll be giving my talk on today, and recent revelations that are causing us to rethink how we think about antibiotics. So what is bacteria? Because many people don't even know the difference between bacteria and viruses. See, this is a bacteria, or a kind of bacteria. It looks simple, right? Very unassuming. But the things it can do are immense. Okay, imagine you're an elementary school student, and you are playing in a playground. You're just going on the swing, up and down, up and down. But then one swing, you go a little too high, you fall off. You fall on the ground, you scrape your knees. You think nothing of it, a little bit of bleeding. The next day, you see a little bit of yellow. Still, it's fine. At least in modern terms, it would have been fine. But you see, back then, that could have been a death signal. You could have been in a coffin within a month. Yeah, it was that easy to die. So what happened? What was a critical difference or the change that was so historical? Well, it was the invention of the antibiotics by Alexander Fleming. And the first antibiotic, penicillin, was so significant that after finding a method of mass production, it was just thrown everywhere. And a good example is World War II, where penicillin was the soldiers practically showered in penicillin. But there was a problem. The problem is that bacteria, much like humans, can adapt to their environments. Now, why is this an issue? It's an issue because we're running out of methods. You see, antibiotics was the first real method we had in being able to combat bacterial infections. And without it, we'd be back to the Victorian eras. And so the fact that they're developing resistances is a really pressing issue. So what did the scientists try to do? We tried to make more antibiotics. We made various types. And of course, bacteria, we were just not fast enough for the bacteria. And they just kept developing more and more resistances. Nowadays, there are bacteria known as superbugs that are resistant to all forms of antibiotics present today. But there is hope. You see, there was a review published by researchers at the Indian Institute of Technology, Delhi, that reviews a plethora of investigations that all point to one thing: a connection between epigenetics and and antibiotic resistance. Why is this significant? It's significant because it helped us identify a very big portion of how bacteria gain and spread their resistances. And this helped us rethink how we can actually combat this imminent threat. So a good example, while there are many methods and connections between epigenetics and while there are many connections, one example is the methylation process. Essentially, when a methyl group is added to adenine, which is a base pair in your DNA, in some cases it helps increase the rate of transcriptions. But wait, what is epigenetics? See, epigenetics is the dial. Think of it as the tap on your sink. If you turn it, more water comes out. If you turn it the other way, all the way, no water comes out. And it's a similar process with genes. Essentially, it can control the rate at which genes are transcribed. So as you can see, the red part is the methylation group. And essentially what this does is it increases the rate at which the gene is expressed. Now imagine if that gene was responsible for, say, horizontal gene transfer. And horizontal gene transfer is a method in which, say I'm a bacteria, and there's a bacteria next to me, and I somehow, out of pure chance, managed to gain a resistance to, say, penicillin. And the bacteria next to me doesn't have it. What can I do? I can transfer that part of the gene to the bacteria so we are both resistant. Now imagine if a protein that was indirectly responsible for this process was the rate at which it's expressed is increased. You can kind of see how this can be a problem. This can exponentially increase the rate at which resistance is spread among not only the same bacteria, but across different species. So then why is this important? Why does this matter? Because this gives us hope. You see, if we lose this battle, that scrape on your knees could have been your last. So this is very significant and very pressing. But once again, why does this matter? Because this research, this connection between epigenetics and bacteria gives us a trajectory on what to work on. And we now know what we can actually focus on to eliminate this issue. But also, it's important because the people who will be finding the actual practical ways of using this knowledge is all of you listening. It's the future innovators, the leaders, who will be able to identify and research and take on the torch and take it to new heights, to places nobody's ever thought of before. And if any of you take anything from this talk tonight, remember that behind every innovation, every convenience, every scientific advance, there's a person and a story. And know that the next story could be yours. Thank you.